Today we'll be considering direct sums of linear subspaces, and we'll begin with the fact that the sum of two linear subspaces is said to be a direct sum if the two subspaces are linearly independent. That is, linearly independent meaning their intersection only includes the trivial set, namely the zero vector. In that case, we write v1 direct summed with v2. Any vector in the normal sum of v1 plus v2 can be written as the sum v is equal to v1 plus v2, where the vectors v1 and v2 are in the subspaces v1 and v2 respectively. This is by the definition of the sum. However, any vector in the direct sum of two spaces can also be written of these, but in this case, this decomposition is considered unique. That is, since these subspaces are linearly independent, you can only write this v in exactly one way, as a sum of v1 plus v2. We can check this because if we had two possible constructions for v, namely v1 plus v2 and w1 plus w2, where v1 and w1 are from v1 and v2 and w2 are from v2, where we have they're linearly independent in the sense that their intersection is the trivial set, then we know that v1 minus w1 is equal to w2 minus v2 is equal to zero vector, since it must be in their intersection. Therefore, we can conclude that v1 is equal to w1 and v2 is w2, so we have a unique representation of v as a direct sum. Or we have a unique representation of v within the direct sum vector space. We can make a complement to this in the sense that to any two vector spaces v1 and v2 over field F, that can be associated another larger space v that is the direct sum of these subspaces, where vi prime is isomorphic to vi. So for instance, we let v be the set of pairs of v1 vector and v2 vector, where v1 and v2 are taken from the vector spaces v1 and v2. Important thing to note is that these vector spaces are full-blown vector spaces. They're not subspaces of some ambient space. They can be like full-blown vector spaces. For instance, v1 can be the set of all vectors of length 3 over the field, while v2 could be the set of all polynomials of degree 3 or less over the field. And these are two completely different full-blown vector spaces, and we can construct v as just taking an element from v1, so a string of three vectors, a string of three scalars, and then have v2 be a polynomial, which you can identify uniquely by its coefficients. We then get that this set of pairs has the structure of vector space over v, where we have the sum defined as just element-wise, in the sense that you take the first elements of each pair and add them, and then put that against in a pair with the second elements of each pair, the sum of the second elements of each pair. And we define the scalar product in the standard way, namely you put it on each element independently. We can then verify that v is equal to v1 prime direct summed with v2 prime, where v1 prime is simply the set of all vectors in v, where the second element is 0. That is, we construct this, we have two full-blown vector spaces v1 and v2, and we construct a new vector space v, which consists of all pairs of these, and then we consider two subspaces of this new space v, and the two subspaces we call v1 prime and v2 prime, and they're defined by, well, v1 prime is just the set of all v1s, or the set of all elements in v, where the second element is 0 and the first element is an element of v1, and then v2 prime is just the set of all elements in v, such that the first entry is 0 and the second entry is an element of v2. We then note that each of these is isomorphic to the original v1 and v2 we started with. That is, v1 prime is isomorphic to v1. They have the exact same structure. This vector space, as we construct it, is called the direct sum of our two vector spaces v1 and v2, right? These are full-blown vector spaces, not subspaces, and we can make a direct sum space, or we sometimes call it the exterior direct sum space. And we write it as v is equal to v1 direct sum with v2 as an abbreviation, which is a little confusing because you might think the v1 and v2 are subspaces of v, but in this case they are full-blown vector spaces in their own right, and then you extend them to construct this new v. Meanwhile, the direct sum operates as normal on normal subspaces. However, sometimes you call the direct sum of two vector spaces in this way the product of these vector spaces, and this is denoted by v1 and v2 times v2. It is, of course, possible to consider this for more than 2 vector spaces in the standard way. For any binary operation, you can always extend it to multiple things if it obeys certain properties. And in this case, you can check very easily that to do the direct sum of 3 spaces, you do the first 2, and then direct sum that new vector space with the other vector space you're considering. I'll leave it as an exercise to you to consider whether or not this is associative. This idea of direct summing things is associative. All right, with that, we've completed a discussion of direct sum vector space in the abstract. I'll see you next time when we consider spans and linear dependence.